So now, so the proportion of students who buy hard copies of textbooks is found to be 0.42. We use a sample of size 12 from last time. The class wall confidence interval happened to be 0.14 less than p less than 0.70, not 70. We want to find a 95% first Wilson interval, second Agresti-Coull interval. So for both of them, we need to find the Wilson estimate. Which is P tilde. Yes. We know the formula for P tilde. We derived it. B plus 0.5 z squared alpha over 2 over n plus z squared alpha over 2. If the sample proportion is 0.42, what is the number of successes? Well, when we started this problem last time, we actually had the number of successes, and I believe it was 5. So B from last time is 5. Another way of finding this is simply take 12 and multiply 0.42. That's 0.42 times 12, approximately 5. We have B. What is Z sub alpha over 2 from last time? How did we find that critical? What did we use? So we can use inverse norm. Area below, in this case, the area below is alpha over 2. 0 and 1. Alpha is 0.05. 0.025. 0.05 divided by 2, 0.025. That will be negative 1.96. But when we find the confidence interval, we take the absolute value. Here, we're squaring, so the negative is going to go away. Yes?
What's 0 and 1 in the inverse norm?
The mean standard deviation. So, P tilde is 5 plus 0.5 times 1.96 squared, ignoring the negative because it's going to go bye-bye when you square, divided by 12 plus 1.96 squared. And what do we get? 4. So subtle difference, small difference, but difference nonetheless. So P tilde is 0.44, which would imply Q tilde, once again, approximately would be 0.56. 1 minus P tilde. The next step is we need to find B star. So in order to do that, we've got to find B star squared. The formula is P hat, 1 minus P hat. P hat, 1 minus P hat. Let me write it as Q hat to save space. And first weight n over n plus z squared alpha over 2. 1/2 multiplied by its complement, 1/2. 1/2 times 1/2, 1/4. Correct? So we will have 1 over 12 plus 1.96 squared. B hat is 0.42. Q hat is 0.58 multiplied by n, 12 over 12 plus 1.96 squared. Second term, 1/4 multiplied by 1.96 squared divided by 12 plus 1.96 squared. Good. Don't be hasty. Do it one term at a time and tell me what you get. Right. So last time, the margin of error was 0.28, which would mean approximately the standard error would be 0.14. So this time, V star squared is 0.15, 0.0154. So V star is approximately 0.012. Yes? No, 0.12. Yeah, my bad. Bad math there. Should go back to algebra. Good. Now we know how to find the Wilson interval. Wilson interval is simply P tilde minus critical value Z alpha over 2. Well, let me write it up there. P tilde minus the absolute value of the critical value times V star P tilde plus absolute value of Z sub alpha over 2 times V star. Correct. So over here, we get 0.44 minus 1.96 times 0.12 less than P less than 0.44 plus 1.96 times 0.12. Good. Don't forget, we've got to put P tilde. This one?
Yes.
That is the margin of error.
Margin of error for the Wilson.
Yes, for
Whatever that
V
is.
star, yes. So margin of error for the Wilson case is P tilde minus its margin of error. And you add and subtract from P tilde, you get the interval as 0.21, less than P, less than 0.67. Very close to Laplace fault, correct? Yeah. Now, when you do this on an exam, homework, whatnot, you do it in a calculator, and if this answer is way off from what you have up there, then you're doing something wrong. You know, they have to be close in some way. The Agresti-Coull is easier. It's P tilde minus absolute value of that inverse norm, square root of P tilde Q tilde over N. That would be the Agresti-Coull standard error, less than P, less than P tilde, plus absolute value of Z sub alpha over 2 times P tilde Q tilde over N squared root. So 0.44 minus 1.96. P tilde is 0.44 and Q tilde would be 1 minus 0.44. So 0.44 times 1 minus 0.44, 0.56 divided by 12. And we can't leave it as is, we've got to take the square root. So square root of that value is 0.1432. And what do we get when we evaluate this? On this side, .1593 So approximately 0.16. And on that side, point 0.72. Good. So once again, that value is very close to Laplace fourth, but given the choice between Laplace fourth, which is 0.14 to 0.70, Wilson and Agresti-Coull, which one should you report if you're reporting to the public? At best, you've got to go with those two. I believe theoretically this is better for a small sample case because it's derived from Wilson, but the Klomper interval is the best, which I'm not going to do here. Yes, good, okay, good place to stop.